That doesn't work in algebra. Nice.
Okay. Okay, these are mine now.
Nice.
These are red beans.
Beans.
Beans with some bean juice.
Everything revolves around beans. The sun is a bean.
The sun is a bean. That's
Really? Nothing else
and differential equation.
online?
I know.
I'm clocking out of that. I'm done.
Look at this thing in college.
Next year, I'm like kind of coasting.
So did you do that? Next time, what do you think? Open heart surgery.
I still have 3
Yeah, but like the classes are like you're the last.
Yeah, next year I'm gonna
Depends on what time they're offered.
No, but yeah, but that doesn't come out as like May for spring.
next year I'm taking
Right?
regular
Unless
English,
you're planning on taking them at the same time.
regular English, stats, AP Psych, AP Order. That's all.
No, I want to say Orgo.
No, I'm doing
Finance.
yeah.
I'm
One
waiting
of
for
the-
the. I'm gonna take Orgo.
Do what?
You, Devin Wilson. I'll take Orgo. He's like one of the best students you have.
Oh
right?
my God, it's another embarrassment.
Let's go this way.
I guess you can't say that out loud. How do you have a life?
Yeah.
It's the same person every time.
Oh, I missed. I'm not.
What is that?
A hair
There
thing,
was some in my seat.
Hair? Or like a hair thing?
like a hair thing.
The
Yeah,
skin
hair things are.
The thing, you put in your hair. We're not sure about that.
It's a comb.
I think you ate the hours. I don't know. I was drinking with bean juice. I was smoking it on the bean juice. Bean juice. Give bean juice. Bean juice is going. Would you try bean juice for $10? No. I would yap on the spot. It's $10. Oh.
All right.
I don't know if you use it. Yeah, I do $10.
You guys have problems that due Friday. Tomorrow is a tutoring day, so you guys can always ask questions tomorrow. You guys can ask questions at the end of the lesson today. Otherwise, your test is not next week, but the week after that on Tuesday. So next Monday, we'll have our last lesson that's on that test. We will have another lesson between then and the test that's not on the test, just because that's where it fit. But we'll have our last lesson that's on your test on Monday, and then you'll basically have a full week to figure out the review, ask questions, figure out what you're not understanding before that test that is the following Tuesday, April the 6th. And then we'll be in our last kind of chunk. That test is going to be over lessons 19 through 26. Yeah. So today we are doing, that is your, there is one more. We'll have one more at the very end of April. That'll be it. May we'll have a final project that you guys will work on where you have time to do so. So you'll have more time than you really need for it, but it'll be like AP tests and stuff will be going. So kind of when you have a chance, you will be able to work on that. It's the one project that you really can do with remote students pretty easily, because they're not like building anything or making anything. It's not. Well, I used to do a MATLAB projects as well, but with this one is like you'll try and research where one place that what we've done is used in some field that you're interested in. Computer science, engineering, people have done medical field, economics has them. Yeah. So anyway, we'll get to that later. Today we're doing positive definite matrices. This goes with our symmetric matrices. These are a specific type of symmetric matrix. So positive definite matrices are just a subset of symmetric matrices. So if you're trying to identify if something's positive definite, first, just make sure it's symmetric. If it's not symmetric, it is not positive definite right off the bat. Positive definite is a specific type of symmetric matrix. They're defined as a symmetric matrix with positive eigenvalues. A positive eigenvalue. Someone in second period started working on the problem set and said, does 0 count as positive? It does not. Positive eigenvalues means positive eigenvalue. So you could always just find the eigenvalues if you want to know if something's positive definite. That is usually not the easiest way. So there's other ways to identify it. That'll be the main focus of today's notes, is how do we tell if something's positive definite. We'll have kind of a brief application at the end for today, but otherwise, mostly we're going to be focusing on like identifying them. First way is to find what we call the upper left determinants and verify that they are all positive. So in a 2x2, remember that it's symmetric, so it'll be A, B, B, C. What we mean by upper left is starting in the upper left, make a 1x1 square, a 2x2 square, a 3x3 square, a 4x4 square. So in 2x2, there's only 2 of them, right? Oops. I would have the 1x1 A, which literally just means is A positive. The determinant of a 1x1 is the number. Okay, then you do the determinant of your 2x2, starting in the left, top left corner. If it was a 3x3 or a 4x4 or 5x5 or whatever, you're basically making a 1x1 square, a 2x2 square, a 3x3 square, 4x4 square. Okay, and you just keep on going as big as your matrix is. Mostly we do 2x2s or maybe some 3x3s, so you don't have to really worry about getting it getting huge. But that's what we mean by upper left determinants. So starting in the left, upper left corner, make a 1x1 square, a 2x2 square, a 3x3 square, a 4x4 square, and you just want to verify those determinants are positive. Really easy for a 2x2, right? We can do a 2x2 determinant pretty quickly and easily. This tends to be my method of choice for determining positive definite matrices for 2x2s. 3x3s, if there's some zeros in there, this is not bad. If there's some zeros in the matrix, 4x4s, this is, I probably would not do this. Because again, we've seen what it's like to take the determinant of a 4x4. 4x4 will turn into a bunch of little 3x3s, which will then turn into a bunch of little 2x2s. So it's possible, it's not super difficult, but it is lengthy. There's a lot of stuff going on there. So this is one way to do it. For 2x2s, this is a really easy way. Okay, another way is finding the pivots. And if the pivots are positive, the eigenvalues are also positive. This is probably what I would use for something larger than a 2x2. Because we can find the pivots fairly easily. We've had a lot of practice doing elimination and finding pivots. Been doing that since the first couple weeks of the semester. So you literally just do elimination, look at the pivots, and determine if they're positive. You have positive eigenvalues. If they're negative, you have negative eigenvalues. Make sure that you're finding this only through elimination. Don't start switching rows and multiplying rows by things. You just want to add or subtract multiples of rows from a single other row. So you could take row 2, for example, minus b over a times row 1, which is what I did here. But don't take a times row 2 minus b times row 1. You're now altering the values of the pivots. So don't multiply rows by things and stuff when you're doing it this way. The problem will be that you might multiply by a negative or something, and then obviously you're changing the sign of the row from what it should be. So I would not multiply rows by, just do strict elimination if you're going to do it this way. The other upside of finding the pivots is that in a symmetric matrix, not only do positive pivots mean positive eigenvalues, but the number of positive pivots is the same as the number of positive eigenvalues. So if you have 2 positive pivots and 2 negative pivots, you'll have 2 positive eigenvalues and 2 negative eigenvalues. If you have 1 positive and 3 negative pivots, you'll have 1 positive and 3 negative eigenvalues. So it'll actually show you the sign of all of your eigenvalues if you find the pivots. For most of what we do, you don't really need that information. We more just need to know, are any of them positive? I mean, are any of them negative or not? But this will give you a little even more information than that. Again, only with symmetric matrices. None of this stuff really applies if your matrix is not symmetric. All right, so we should be able to answer a simple question. Does this matrix have negative eigenvalues? Obviously, one way would be to find the eigenvalues, which we can do, and that's not super hard on a 2x2. Okay, we've been doing that now for multiple lessons in a row. Option 2, you could find the upper left determinants, which again would just mean the determinant of the 1 by 1, 1, which is just the number. Okay, that's just 1, which is positive. So that first determinant, it's literally the number. Then the next one would be the determinant of 1, 2, 2, 3, which is 3 minus 4, which is negative. This means A is not positive definite. And A has at least some negative eigenvalues. Option 3 would be to do elimination. So if I take 1, 2, 2, 3, I could take row 2 minus 2 row 1. Then I would have 3 minus 4 is negative 1. Look at the pivots, and you can tell A has 1 positive eigenvalue and 1 negative eigenvalue. So yes, okay, if we found the eigenvalues, we would see there's a negative 1. If we use the determinants, we would see we have negative eigenvalues. If we do the pivots, we can see that we have at least 1 negative, well, we have exactly 1 negative eigenvalue. So any of those would work. You don't have to do all 3. Okay? You kind of do whichever one you're most comfortable with, you find the easiest. Option 2 and option 3 in a 2x2 are pretty similar difficulty. Neither one is very, very difficult. So you can just choose there. Okay. The one application that we're going to look at today is with a positive definite matrix. If I start looking at its eigenvalues and eigenvectors, AX equals lambda X. If I take that equation and I multiply by X transpose on the left-hand side, what I'm going to get here is X transpose times lambda times X. Lambda is just a scalar, so I can pull that out front and get lambda times X transpose times X. We went over this a while back when we were doing projections and things like that. This is the dot product. This is just X dot X. Okay, written in matrix form, it's a row times a column will give us one single number. A 1 by 5 times a 5 by 1 will give us a 1 by 1. That one number is the dot product. So again, X transpose X, that's just X dot X, which is the magnitude of X squared. Right, when we take a dot product of a matrix in itself, we're basically squaring all the elements, adding together All we'd have left to do is take the square root and we'd have the magnitude of that vector. Well, if we look at this, this part is definitely non-negative. Right, we find the magnitude and square it. We might get 0 if the vector is the 0 vector, but otherwise you're going to get a positive value there. If A is positive definite, then lambda is positive 2. Right, this would be a positive number 2. This means X transpose A times X is positive. Okay, if lambda is positive and the magnitude of X squared is generally going to be positive, it could be 0. Then as long as X is not the 0 vector, X transpose A X will be positive. Okay, this matters because this is a way for us to analyze polynomials for some similar things that we can find using calculus, we can find here using algebra. So if we look at X transpose, okay, it'd be a row vector with the variables in it. A would be a symmetric matrix. And then X would just be a column with the variables in it. If I multiply this all out, I'll get a polynomial. In this case, I'll get a 4-dimensional polynomial. If you do a 3 by 3, you'll get a 4-dimensional one. The size of your matrix is going to be the number of independent variables, right? Because we're multiplying by X, Y, and Z here. So I'm going to have W equals a function of X, Y, Z. If we do a 2 by 2, we have a 3-dimensional function. But what we're going to get is the main diagonal here. These are the coefficients of X squared, Y squared, and Z squared. If we were to multiply this out, right? A is in the first row, first column. So when I multiply on both sides, each time it's going to be multiplied by an X. When I multiply the row times this, I'll get A times X. And when I multiply by the column, then I'll get another times X. So that's going to be AX squared and dy squared and FZ squared. Okay, that main diagonal will be the X squared coefficient, the Y squared, Z squared. And if there are more variables, you just go down the diagonal, and that's the coefficients of all the squared terms. Each of the other ones, so like B is in the second row, first column, and in the first row, second column. So B is the coefficient of the first and second variable, because both times when I multiply, it's going to be multiplied by the X and the Y. But since there's a B in both locations, you're going to get 2 of them. C is in the third row, first column, and first row, third column. C is going to be multiplied by the first and third variable. So 2CXZ. And then E is in the third row, second column, and second row, third column. So that's going to be the second and third variables. Okay, and so we get this polynomial. It's always going to be second order, meaning squared things. So like kind of quadratic, kind of parabola-ish things. But like this one's 4-dimensional. If we had a 2 by 2, we'd have a 3-dimensional, which is the ones we're mostly going to see in our homework and our tests and stuff like that, is 2 by 2s, which would mean a 3-dimensional function. So as long as A is positive definite, we know this function is positive, except at X, Y, Z equals 0. So technically greater than or equal to 0. It has an absolute minimum at 0, 0, 0 when A is positive definite. Okay, it means the only place it's 0 is when X, Y, and Z are 0, and it's never negative. So we can kind of start to analyze these certain types of functions, these polynomials, second order polynomials, using matrices, and look at things like absolute minimums, look at things like positive versus negative values on the function. We'll tend to do a lot of 2x2s. So A is positive definite when X transpose AX is positive, as long as my vector X is not 0. Okay, in which case it would be 0. And so our polynomial that we'll mostly see in everything, again, A is just going to be the X squared's coefficient. C would be the Y squared, and then 2B would be the XY coefficient. So that would be our function. And we're just saying as long as X and Y are not 0, this thing will be greater than 0. When X and Y are 0, it will be 0, and it will never be negative. So we can kind of algebraically analyze a function in similar ways that we did with calculus, finding maximums and minimums and stuff like that. Okay, and that's mostly the new information for today. We'll do a couple examples. This is just a summary of what we just did. Okay, if I'm trying to determine a positive 2x2, make sure it's symmetric, which I forgot to put in here. To determine if it's positive definite, either find the eigenvalues. If they're positive, it is. Find the upper left determinants. If they're positive, it is. Find the pivots. If they're positive, it is. Or if you know anything about the function, okay, if we already know that it has no negative values, or if you have graphing software and you could see that it has no negative values, that would be another way you could tell A was positive definite. Generally, number 4 is something we are trying to figure out using that fact, not something we are using to figure it out. So like on your test, I would expect to have something where you can figure out one of these 4 things and use that to answer something about the other. So maybe I have a way to tell that I have positive eigenvalues, and therefore I can tell that this function is positive, or I have a way to tell that this function is positive, and therefore I know the pivots are positive, or whatever. Okay, these are all essentially equivalent statements in a symmetric matrix. Okay, it has to be symmetric. That's the only way this is true. So I would make sure these are written down. These are the same things we just went over. So if you wrote them down there, that's fine. But just make sure you have them written down. You have open note tests, so you can use this information if you forget it. All right, so is A positive definite? And what does that mean about the function x squared plus 4xy plus 7y squared? Okay, so you could choose whatever way you want to figure out is A positive definite. I'll use determinants. So determinant of 1 is 1, which is positive. Determinant of 1, 2, 2, 7 is 7 minus 4, which is also positive. Which means A is positive definite. What that means is that 0, 0, 0 is the absolute minimum of f of xy. Okay, or f of xy has no negative values, or I don't know, it's greater than or equal to 0 or greater than 0 everywhere except at 0, 0. However you kind of want to say that, what we would know about that function is it has all positive values except for at 0, 0 where it is 0, but no negative values. Okay, technically, algebraically, we could also figure this out. Okay, if you wanted to figure it out and use that to kind of go the other direction, you technically could. We could complete the square and see that there's no way to get any negative values here. So if we have x squared plus 4xy, if I divide 4 by 2, then square it, that's 4y squared. But I need a 7y squared, so I'd have to also add 3y squared to kind of balance the equation. That makes those first three terms a perfect square. X plus 2y squared plus 3y squared. And so you'd be able to see that I have a non-negative here plus another non-negative number, which means there's no way for that to be negative. And there's really only one way for it to even be zero. If I have two non-negative numbers and add them together, the only way I get zero is if both are zero. And there is no way to get a negative number if I'm going to take a squared number plus a squared number. I'm going to get generally positive numbers unless both of those numbers happen to be zero squared, where I'll get a zero. So we could use algebra, okay, to show this. We could use calculus as well. We could find the minimum, and what you're going to find is that it's at 0, 0, using calculus. So you could do that, but linear algebra wise, this is all you guys need. Okay, to answer the question that's being asked, that's kind of all you would need there. All right, same kind of question. Is this positive definite? What does that mean about the function? This time I'll use the pivots just to show a different way. So I'm going to take row 2 minus 2 row 1. And I get 2, 4, 0, and then what, 3 minus 8 is -5. So I have 2 and -5. A is not positive definite. This means f of xy has negative values. Okay, it means the minimum is not at 0, 0. Although it is 0, 0 makes this 0. There are values that are lower than that. Okay, so these are kind of our paraboloids that we saw in multivariable calculus that we're kind of looking at. So these are the paraboloids, and we can kind of tell if 0, 0 is the minimum, if 0, 0 is not the minimum. Here, 0, 0 would not have a minimum. There are negative values where it's going to go lower. And again, if we use just kind of normal algebra, we could kind of see that here. This kind of normal, when I say normal algebra, this works really well with two variables. It would get more difficult to kind of figure this out with more variables, but you could do it. So I'm going to complete the square again. I'm going to factor a 2 out because it makes it easier. Divide 4 by 2 and square it, and that's going to be a plus 4y squared, which means I have 8y squared, but I should only have 3y squared. So to balance, I'm going to have to subtract a 5y squared. So this is 2 times x plus 2y squared minus 5y squared. This thing is not always positive, right? This, I have two non-negative numbers, but because I'm subtracting them instead of adding them, now I could find other things that make it 0, maybe. I could even find other things that make it negative, other than just 0, 0, 0, which does make it 0. But I could see here there are ways I could start kind of plugging in numbers and finding numbers that are smaller. I could probably plug in numbers and find other numbers that would make it 0. So that we can tell by A being not positive definite. We know that that's going to happen, okay, with whatever the function is there. Okay, going the other way, which is more likely what you would want to do, is I see a function and I kind of want to know about that function. I would come up with my A matrix. The diagonal values are the coefficients of the squared terms. So like 1 and 3, the x squared and the y squared coefficient. The other two numbers are going to add up to give me the 8xy. It should be symmetric, so they should be 4 and 4. And so if I look, I have one positive determinant and then 3 minus 16, which is not positive. A is not positive definite. So f of x, y does have negative values. And there's other ways to show that. There's other ways to figure that out. We can use linear algebra as one of those methods. Okay, you could probably use calculus. You could probably just use algebra and completing the square and whatever. And again, we mostly will do 2x2s. You could see a 3x3 in the homework or the bonus or whatever like that stuff is. It's just going to be higher dimension second order polynomial, still squared. Okay, and then for n by n matrices, the same exact tests will work. So if I had a 3x3 or 4x4 or 5x5, I could either find the eigenvalues, as long as they're all positive, it's positive definite. I could find the upper left determinants, which again, there will be as many of them as there as n. So if it's a 3x3, I'll have to find 3 determinants, a 1x1, a 2x2, a 3x3. If n is 5, I'll have a 1x1, a 2x2, a 3x3, or 4x4, or 5x5. I can find the pivots, which is what I tend to use if it's large. And again, this function, which will now be a higher dimension, it's n plus 1 dimensional function, is positive except when x is 0. All 4 of those things are the same. All 4 of those are the same thing I would do with 2x2s. It's just that the larger it gets, the more I probably would do number 3 there to figure out that the other ones are also true. All right, so 3x3. I'm going to do both, finding the pivots and finding the determinant. Again, you only choose one or the other. So here I would take row 2 plus 1/2 row 1. So again, don't take 2 times row 2 plus row 1. If you start multiplying rows, it's not that it will always mess it up. It's that you could do something that's going to influence the sign of the pivot in a different way. So I wouldn't start multiplying rows by anything. Take single rows and add multiples of other rows, and that's okay. You won't keep the determinant this. Oh yeah, yes. The determinant will stay the same. I was thinking eigenvalues, but yeah, it's basically to keep the determinant the same. All right, so we add the rows. I get 0. I have 2 plus a negative 1/2 is 3/2. -1, 0, -1, 2. And now I'm going to take row 3 plus 2/3 row 2. So this is the only time that pivots can be kind of annoying, is you might end up with fractions since you don't want to multiply rows by anything. So I have 2, -1, 0, 0, 3/2, -1, 0, 0. And then thirds. So I have 6/3 minus 2/3 is 4/3. So I look at my pivots. And they're all positive, so A is positive definite. Okay, I could do my determinants. My first one is just the determinant of 2, which is 2, which is positive. Then I'd have the determinant of 2, -1, -1, 2, which is 4 minus 1, which is 3, which is positive. And then I'd do the determinant of the whole thing. So to do that, we'd pick a row or a column and do our cofactors. So I have 2 times the determinant of 2, -1, -1, 2, minus a -1 times the determinant of -1, -1, 0, 2, plus 0 times the determinant of -1, 2, 0, -1, which we obviously don't need that one because it's 0. This would be 2 times 4 minus 1 plus -2 minus 0, which that's 6 minus 2 is 4, which is positive, 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 positive. So A is positive definite. So to me, the determinant one is going to get more and more complicated the larger it gets. Again, it's not that it should be hard to do. You're just multiplying a bunch of numbers. But the larger the matrix gets, the more you're going to have a bunch of those numbers you're multiplying and adding together. Yeah, I mean, a computer can find the determinant. Your calculator has a determinant function probably on it. So if you have computing software, then sure, yeah, the determinants probably would be the easiest way to do it. Some computer programs might be even just able to tell you if it was positive, definite or not. I don't know. You certainly could write a program that would tell you that doing one of these things. All right, last thing is probably more useful in proofs, which we don't tend to do a lot of proofs in here, but sometimes a homework will have something that you're either proving or explaining something, or the bonus sometimes has proof type things. So these would be useful for that. But also just anything you see proofs of different things, they will use these types of facts here. So if you have two positive definite matrices, when you add them together, you will get another positive definite matrix. Also, ATA, which we've talked about before, A transpose A, which we talked about actually maybe the first week of this semester, is square and symmetric, which we've already said, but it actually ends up being positive definite too. So whenever I do that, which we've seen that in a few of our formulas, ATA in there, but in general, if you ever multiply A by its transpose, you'll get a square, symmetric, positive definite matrix. And that's where we're going to stop today. We still have about 10 minutes. If you guys have any questions or need anything, otherwise tomorrow is also a question day. If you guys need that, make sure you start the problem sets so that if you do have questions, you can ask those. Problem sets due Friday. We have a new lesson also Friday. But yeah, if you guys need anything, let me know. If you don't, you guys have a good rest of your day, and I'll see you guys tomorrow.